Hi. Hi, guys. How are you? I wonder if you can hear me. So, uh, as you can tell, I am not quite in a position to do a live solve today, but the good news is that I'm actually just the host. Hi, everyone. Welcome to our channel. I'm Po-Shen Loh, and I normally work at Carnegie Mellon University, although right now I'm in Bellevue, Washington, which is right by Seattle, because I just got off a plane, actually from Shanghai. But I just want to say welcome very much. Welcome to everyone. Thank you very much for coming to our live solve today because we love working with Math League. It's always good to have a frequency by which you can do interesting problems. And the Math League folks do this every single month. They come up with a good problem set. If you haven't done if you haven't done Math League before, I strongly recommend it's mathleague.org, O-R-G. You can register and you can do monthly contests. And then we'll always go over the solutions afterwards. Since I won't actually be the one presenting, I just wanted to say hello. I'll actually be handing it off to two wonderful people, Arush, who's from New Jersey, and Dorothy, who goes to school at Oxford. But I'm guessing she's actually at home in California right now. But with that, I'll pass off. So nice to see you all. Have a great live solve.
Thank you so much. Wow, guys, I'm super excited. What about you, Dorothy?
Yeah, I'm so excited for this. I think we're going to get started with some quick introductions and then we're going to jump right into the problems for you guys. So I'll start by introducing Arush. Arush is a high school junior from New Jersey and an officer of his high school's math club. He's a USA JMO qualifier who loves not only competition math but sharing it with his peers. Aside from teaching his classmates and neighbors using the knowledge and experience he has picked up from competitors like HMMT, AMC, and AIME, he also participates in Science Olympiad, Science Bowl, self-guided machine learning projects, volleyball, and attended Mathali in 2024.
Wow, thank you so much, Dorothy. That's really nice of you. And I also have something to say about Dorothy, too. Dorothy grew up in San Francisco, California, where I've always wanted to visit. I think I've gone once. I wanted to go again. And she's now a freshman at Oxford studying math and philosophy. In high school, she was a four-time Emmy qualifier, a science Olympiad and cross-country captain, and a soccer referee, which is really cool. Me personally, though, I like basketball more.
Oh, really?
She attended MMSS and HCSSIM, and she's a big fan of the number 17 and its multiples. Dorothy loves learning languages, playing the violin and the viola, and sometimes the kalimba and the piano. Dorothy, you have to tell me what the kalimba is. I actually don't know what that is. And she also likes hiking with friends, crocheting, cartography, cooking, crosswords, cryptography, I'm guessing other things that start with C, alliterations, and things that telescope.
Yeah, thank you so much for that introduction. For anyone wondering, a kalimba is a percussion instrument where you pluck these times. It sort of looks like a piano, but you can hold it in your hands. It's a very cool instrument. I recommend looking into it.
Wow, a handheld
Yeah,
piano. I would love that.
I think it's
So
time for us
cool.
to start the live solve, if you guys are ready.
Well, actually, before that, why don't we ask a quick icebreaker? It might be a little bit hard to see on my screen, but how was everyone's break? I'm assuming most of your breaks have ended, and we'd love to know in the chat, what are cool things did you like it? Did you sleep a lot? I slept a lot.
Mine is not over yet, thankfully. It will end on Tuesday. Ooh, Sunny is wondering if I can play Isai's Violin Sonata 3. I actually haven't tried that one. I've played some similar sort of romantic concertos and stuff, but haven't tried that one. Oh my gosh, someone went to San Francisco for their break. That is so
Ooh,
exciting.
wow,
I
it's a
hope you
fun
like it.
coincidence. I'm jelly.
Someone rolled down a
Break is kind of
snowball.
fun.
That's fun.
Wow. Wait, I have a question. Did you turn into a giant snowball? I've always seen this in comics and like TV shows, but really curious.
Oh yeah,
We've
that
got a
is definitely a
cruise,
caricature.
Ottawa. Yeah.
Alaska. That would have been pretty cold for this time of year. Or
Ooh,
any time of
Las
year.
Vegas. How is the weather in Las Vegas right now? Is it warm or cold?
I feel like it should be warm. It's been quite warm in California. It was like 80 degrees today where I was.
Really? Wow. Today was
Yeah.
like 50 for us. It's been like 50, 60s for the last few days, which is pretty crazy if you ask me. Oh my god,
Bali is
negative
good.
10 degrees in Ottawa? Ah,
That is
too cold for me.
crazy. Yeah.
Ooh, Florida was nice and warm. You know, in fact, I did go to Florida this break. It's pretty awesome. My brother and I, we went to all three Universal, what is it called? Universal Parks? Yeah. which is really awesome.
Yeah, I've never been to Florida, but I'd like to go. Heard good things about it.
Dorothy, what about you? Did you go anywhere?
I went to Los Angeles, so stayed in California, but it was very nice and warm there.
Cool. All right, so exciting. Everyone went so many
so
cool
it was
places.
-24. That is even colder. Wow, there's quite a range of temperature this break.
That is pretty crazy, yeah. All right, so Dorothy, you want to get this party started? Start the live
Yeah.
solve?
Let's look at the first question. Alright, so this one says Lily has a standard deck of 52 cards, which contain cards of 13 different ranks in each of 4 different suits. She randomly chooses 2 cards from the deck without replacement. What is the probability the cards are of the same suit? Arush, do you want to get us started?
Awesome. So first, let's understand what the question is asking for. We choose 2 cards, and we want to find the probability the cards are of the same suit. Now, a key observation is, it doesn't really matter what the first card we choose is, as long as the second card has the same suit. So, for starters, we can assume we've already chosen one card, and we've seen the suit. Dorothy, what do we do next?
Well, so that means when we have our probabilities, we can just start with a 1, right? The probability the first card of the suit is of the suit we want is 1. And then we can multiply that by the probability that the second card is of the suit we want, right? And so we've already taken away 1 card of that suit, so we have 13 minus 1 cards to choose from out of 52 minus 1 cards. So this 1 here, you could also say is just 52 over 52. Because any card we choose is good, and there are 52 options. So if we simplify this, we're going to get 12 over 51. And then you'll notice both of these are multiples of 3, so we can simplify this to 3 over 17. And I believe that's our answer. Does that look right to you? Oh, 4 over 17. You were so right.
4 over 17.
Yes.
All right, awesome. That was really quick. How do you guys feel about that?
Yeah, I'm seeing a couple other
Got any
417s
answers?
in the chat. That's good.
Awesome. All right. I'm loving the way this is looking so far. Great solve, Dorothy. And let's check the answer. And it is indeed 4 over 17. That is great. All right. How about we get on to question number 2, number 4 in the round. Betsy is building a pyramid with the property that the nth level of the pyramid has n squared bricks. How many total bricks are in the first 7 layers of the pyramid? Wow, that's interesting. Well,
Yeah.
If I want to find how many total bricks there are in the first 7 layers, I can just add up the 7 layers. And that's not that hard of a computation. But then again, this is also the sprint round, and we need to be fast. Dorothy, do you have any ideas?
Well, I'm thinking there is this formula for the sum of the first n squares, so if you know that on this competition, it might be quicker to do that, but if you don't, it's also perfectly fine. I would just add it up instead of trying to derive some sort of rule. Because we only have 7 numbers to add up. They can't get that big. And I think a lot of us hopefully will know the first 7 squares just off the top of our head. We have 1, 4, 9, 16, 25, 36, and 49. Arush, are you just
Oh
gonna
my
go
God,
with this
adding.
up method, or do you have something better?
Oh my god, you're putting it on me? I don't want to add it up. That looks like a pain to add. Oh my god. Well, I mean, you could add it up. And what would you get? You get 1 plus 4 plus 9, so far that's 14. Plus the 16 gives you 30, right? 30 plus 25 is 55. 55 plus 36 is, that's what, 91, right? And 91 plus 49 gives you 140, I think.
Yeah, that's what I got as well.
Yes, exactly what you wrote. Alright. So, we know our answer is 140. But now, Dorothy, I have to ask you. I don't want to find how many bricks are in the first 7 layers. I want to find how many bricks are in the first 15 layers.
Oh no. Well, actually, it looks like Rat Chile is maybe giving us a handy formula in the chat. If you guys look at that,
Ooh, awesome. And it's in latex. Cool, I love latex.
yeah, better formula if you want to find the sum of the first n squares. N times n plus 1 times 2n plus 1 all over 6.
Wow, that's an awesome formula, and it's really compact too, because we no longer need to add up any squares. All we do is multiply a few numbers, divide by 6, and boom, we got our answer.
Yeah,
That's a pretty neat way to do this.
yeah. Alright, well I think we can
And in
move
case
on
you're
to
wondering,
the
guys,
question. Yeah, thank you for all your participation in this question. It's very helpful. So, I think 140 was indeed our answer, right?
yes.
Cool. Next question. How many 3-digit positive integers have a perfect square digit sum and the property that each digit is a non-zero perfect square? So I'm thinking for this one, we can start with the second part. The property that each digit is a non-zero perfect square. Because there really aren't that many of them, right? There's 1, 4, and 9. So where should we go from here, Arush?
Well, we know that we have a total of 3 digits, and each of them is between 1, 4, and 9. And we know these 3 digits must add up to another perfect square. Well, the smallest possible digit sum is created if each number is 1, and 1 plus 1 plus 1 gives us 3. And the largest possible digit sum is 999, which gives us 9 plus 9 plus 9 equals 27. So we know the digit sum must be between, and this is inclusive, it's going to be in between 3 and, now write digit sum, between 3 and 27. And we're also given that the digit sum must be a perfect square. So Dorothy, which numbers are perfect squares between 3 and 27?
Well, I know that 1 squared is 1, so that's too low. 2 squared is 4, so we can start with 4 as our options. Then we have 3 squared is 9, 4 squared is 16, and 5 squared is 25. So that's not that many options to try. And if we're trying to find ones that sum to 4, I don't actually think that's possible, because if we have 1, 1, 1, that sums to 3. And we don't have a way to increase any of these digits by just 1 to get a sum of 4. So 4 is not an option for us. Then if we have 9, I think I see a way to do 9. I think 4, 4, 1 would get us to 9, right?
That's exactly right. And if we tried using 2 ones, then the remaining digit would need to be 7, but we don't have a 7. And of course, if we used a 9, that would be too big. So I think we're stuck with 441.
Yeah. So we can cross off 9. We found one way that sums to 9. Now let's look at 16. 3 4s would only get us to 12. So that means we're going to need a 9 somewhere. So say we have 1 9. Another one would get us to 18. That's over. So we need a 9 and some other things. 2 1s isn't enough. That's 11. And if we do 9 plus 4 is 13, we can either add 4 to get to 17, which is one of my favorite numbers. Great number, but not what we're looking for. Or we could do a 1 and that gets us to 14. So either way, we're not able to get to 16. So we can cross that off our list. What about the last one on our list?
That's an excellent question. Well, I think if all of our digits were 4 or below, then the maximum we could get is 12, which is way below 25. So we know, like Dorothy said earlier, that we must have at least one 9. So we start with a 9. And now we only have to get to 16. But if we add another 9, and we're at 9, 9, we're at 18, and we need another 7. But do we have any 7s left? No, it's only 1s and 4s. So we can't do 9 and 9. Well, what about 9 and 4? Well,
Only gets us to
this actually
13.
doesn't matter.
Yeah.
That does
so
get us to
would
13,
make
yes.
2 enough.
In fact, if we don't add another 9, then the maximum possible maximum possible sum we can have is 8 for these last 2 digits. And 8 plus 9 is only 17. So if we don't include a 9, then we only get to 17. But we just show that 2 9s doesn't work. So we can't get to 25. Does that make sense, everybody?
Makes sense to me. And so that means 441 are the only digits we have. But we can rearrange these. I also saw a really great comment in chat from Tara asking if there are 27 possible ways to form a number. And you're exactly right with that. Because we can put a 1, 4, or a 9 in every place, we have 3 times 3 times 3 is 27 ways to do it. So we could have just listed out all 27 and gone through them one by one if we had wanted to. But I think it's a bit faster to do it this way. So now all we need to do is rearrange these digits. We can have 144, we can have 414, or we can have 441. And so what I'm doing is I'm just moving the 1 around in the different place values. The 1 can either be first, second, or third, but it can't be anywhere else because we only have 3 digits. So that means, I think, that there's going to be 3 possible 3-digit positive integers with a perfect square digit sum and this property. What do you think about that, Arush?
And I also think this is really neat because, keeping up with the theme of perfect squares, guess what these two numbers are? 144 and 441. If I'm not mistaken, 144 is actually equal to 12 squared, so it's a perfect square itself. And 441 equals 21 squared. In fact, when you reverse the digits of 144, its square roots digits are reversed too, which is a lot of coincidences in one problem. I love that.
Yeah.
Too bad 414 doesn't have anything special about it.
Yeah, they can't all be special.
Alright, let's check the answer now. And it is indeed 3. Awesome job, Dorothy.
Yeah. Alright, so we can move on to the next question. The base 10 integer 123 is converted to base 2, and that base 2 representation is then read as a base 10 integer. What is that new integer?
Wow, that's a lot of bases. Well, we first convert to base 2. So now we have some binary string of 1s and 0s. For example, it could be something like 1 0 1 1 0 or 1 1 0 0 1 1 0. In fact, there's lots of possible binary strings that we could have. It just means that we have a sequence of 1s and 0s that represents some base 10 integer. First, let's try to find 123 in base 2.
Yeah.
Dorothy,
so
do you have any ideas on how to do that?
I think the way you typically do that is you just find the biggest multiple of 2 that can go into the number. So I know 128 is a multiple of 2, and that's a little bit too big. So we're going to have to go down one multiple, or sorry, not multiple of 2, power of 2. So 128 divided by 2 is 64. So that's going to be the best we can do. We're going to subtract 64, and we're going to put a 1 in the 64's place. So just like in base 10 we have the 1's place, the 10's place, the 100's, here we have the 1's place, the 2's place, the 4's place. It's kind of strange, but we're going to put a 1 in the 64th place, and then subtracting this, we get 59 left over. The biggest power of 2 that goes into 59 is going to be 32. So we can put a 1 in the 32's place and keep going. Subtracting 32, we're going to get 27. So the biggest now is going to be 16. The 16's place is next, so that works. We have 1, 1, 1. 27 minus 16 is 11. And so then we're going to have a 1 in the 8th place. And then we have a 3. So 3 is interesting because the next place coming up would be the 4's place. But 3 is smaller than 4, so we have to have a 0 in the 4's place, and then a 1 in the 2's place, and a 1 in the 1's place, because 2 plus 1 gives us 3. Arush, does this look right to you?
That looks exactly right. Great job, Dorothy. And so, like lots of people have said in the chat, our final string, also like Dorothy wrote on her board, is 1 1 1 1, 4 1s, a 0, and then 1 1, which is our base 2 representation. So are we actually done? Because we want to convert it to base 10.
Well, I think this is basically already in base 10, right? This looks like it to me. We just need to be able to read it. How would we read this number as a base 10 integer?
Well, it looks like, and that's a lot of numbers to count, 1,100,000, 110,000, actually no, I'm sorry, 111,011. So we already have it in base 10. We just need to think of it in base 10. We wrote out the digits, and we can interpret it in base 10. And so our final answer is indeed 1111,011.
Nice. And yes.
And if we check
I
the
believe
answer,
that's what this says.
that is exactly right. Alright. Let's keep going. We got a triangle now. I love that. Triangle ABC has side lengths AB equals 14, BC equals 16, and AC equals 10. Whoa, stop. Before we do anything, what's the first thing we should do? And I see Dorothy's already doing it.
I think we should draw a picture whenever you have a geometry problem. Even if it's as simple as a triangle, we might as well draw a picture to get a better handle on things. It's okay if it's not to scale.
That's an
Just
awesome
pretty-
idea. Alright, so our three vertices are labeled A, B, and C. And I'm going to let you guys in a little secret. I actually always draw the same triangle no matter what the side lengths are. Don't tell anyone. I always draw the same scaling triangle, like the one you see on my screen right now.
Actually,
We're
I
also
think I
given
did
that
the
AB
same
equals
thing.
14. Really?
Yes.
Oh, but I label
That-
mine a little bit differently.
I label my vertices according to the side length, so I can pretend that I did it on purpose. Like, note how AC is the smallest side, so I assign A and C to that side. But same idea.
Actually, no, I think I'm going to draw my diagram to match Dorothy's, because hers is a lot better than mine.
I wouldn't go for a lot better, but maybe marginally better. Slightly less confusing if we have the same labeling. I see Daniel saying just use Heron's formula. Yeah, I mean, I'm kind of inclined to just use Heron's formula. Arush, do you have anything better to do? Should we bash it out?
I don't think there's a faster way to do it.
Yeah, I think if it's a triangle where you can easily see that it'll divide nicely into two right triangles, or, another way you can easily find the area, go for it. But Heron's formula, it's trusty, this is a sprint round, so let's just do it.
Alright. So, the first step in using Heron's formula is we need to find the semi-perimeter. And Dorothy's already writing S on her screen, which stands for semi-perimeter. Now, the semi-perimeter is simply half of the total perimeter of the triangle. Now, guys, if I add up 10 plus 14 plus 16, that gives me a perimeter of 40. That's right? I can add?
Yeah.
And so 40 over 2, the semi-perimeter is 20. So we can write S equals 20. Now we can use the wonderful formula that Dorothy has on her screen and say that area of ABC, I'm going to use square brackets to indicate area, equals the square root of 20 times 20 minus side length A. And side length A is the side that's opposite vertex A, which has length 16. So 20 minus 16. Now we're going to do S minus B. S, once again, is 20, and B is 10. 20 minus 10. And finally, S minus C is 20 minus 14. Alright, and so now, if we look at our thing, Dorothy's actually already written out all the subtractions. We get this is equal to the square root of 20 times 4 times 10 times 6. Well, Dorothy, do we immediately have to multiply all of this out?
I don't think so. I think the way it's already multiplied is actually going to play to our advantage here, because we can just pull out common factors. So I know 20 is 2 times 10, so I'm going to pull a 10 out of the 20 and a 10 out of the 10 to get a 10 outside of the square root, and then I'll copy down the 2. And then the same idea with the 4 and the 6, right? They both have a 2 in common. So we can put another 2 out here, and then the 4 leaves us with a 2, and the 6 leaves us with a 3. And then we can even pull out these two 2's as well. And so since there's 2 of them inside the square root, there's going to be 1 of them outside of the square root. So we get 2 times 2 times 10 times the square root of 3. And I think this is going to be an easier multiplication problem than if we had multiplied it all out within the square root. So what does that get us as a final answer?
I think that gets us 40 root 3, because 2 times 2 times 10 is 40. So I'm going to scribble down 40 root 3 on my answer sheet, and, oh no, What is the question asking for? Is it asking for a squared b? Or is it asking for a plus b?
It's
Well,
asking,
here, a equals 40. Yeah, sorry?
no, it's asking for a plus b. You'll notice for a lot of math competitions, they don't actually want you to write it in radical form. If you get that, there's often like a weird little trick. Or same with a fraction where they want you to sum things. So here they want a plus b, which is 43.
Alright. Great job, guys. Our final answer is 43, and I think we've got this. Dorothy, can I get a drum roll while I check the answer?
Oh, yeah?
It's 43! Let's go,
Yay!
guys. Alright. Alright, now let's see. A committee with 5 members is voting on a proposal. Each of them has an independent 2/3 chance of voting to approve the proposal. And right here I'm going to stop and circle independent. This is going to be really important. Has an independent 2/3 chance of voting to approve the proposal. Given that the proposal only passes if at least 4 members vote to approve it, what is the probability that the proposal will pass? Express your answer as a common fraction. Now I see Dorothy's already gone ahead and annotated the question, which is really good. A lot of these are actually filler words, and we only need to look at the key terms. For example, we know there are 5 members. 5 members. And there's an independent 2/3 chance of voting to pass it. And we need, the problem says this, we need 4 votes to pass. And see, taking out the key points of each problem is a great way to quickly read over it. You don't need to read every word. You can solve it really quickly if you just get the key points. So Dorothy, take it from here.
Yeah, so the one very key thing that Arush flagged at the very beginning is that these are independent. Most of the time, the probabilities you're going to see in math competitions are going to be independent because that's what's easiest to deal with. But that tells us we're allowed to multiply these to find a total probability. So that is key for how we're going to do this. And it's also important to note that you need at least 4 members to vote to approve it. So that's not exactly 4. So we can have 4 votes or we can have 5 votes. And each of these is going to give us a different case. So say we have 5 votes. I think that's the easier one. So that just means that all of them have to vote to approve it, which means we can do the 2/3 chance that they vote to approve it raised to the power of 5, because we multiply the chance that each one of them votes to approve it by the chance that the other ones are voting to approve it. We have 5 people approving it, so 2/5 to the 3rd, which is going to be 32 over 243. And then, Arush, what do we do with this 4?
Well, so for now we know that the probability that we have 5 votes is 32 over 243. And the probability that we have 4 votes, well, would it just be 2/3 to the 4th times 1/3 to the 1? Not quite, because we also have to choose which member actually doesn't approve it. Well, we have 1 member that's not approving it, and there's 5 total members. So first, I can choose 5 ways to choose who does not upvote it. Now, there's a remaining of 4 people that each need to vote for it. So that's 2/3 to the 4 probability. And the person that we chose to not vote for it has a 1/3 chance of doing so. Now, this product will evaluate to, I think it's 80 over 81. I'm a little bit bad with arithmetic.
I think it's 80 over 243, because 3 to 5th.
Oh, whoops, yeah, I forgot about the last 3. That's exactly right. So, we have our 2 probabilities. And it's important to note these 2 probabilities are disjoint, meaning either we have exactly 4 people vote for it, or we have exactly 5 people vote for it. We can't have both. So, we can simply add these probabilities to get our final answer. And 32 over 243 plus 80 over 243 equals 112 over 243. And thankfully this time, they're just asking for the fraction, not for some weird a plus b thing. So our final answer is simply this. It's 112 over 243. I saw a lot of you guys put 16 over 81, and it's easy to fall into that trap. But remember, it's always good to take a step back and look at different ways to see the problem.
Yeah.
Alright,
And
let's
I
check the
think-
answer. And it is indeed. Yes, sorry?
Yeah, we got lucky there that you can't simplify it further, and it's easy to check because the denominator is only divisible by 3. So we just need to check if the numerator is divisible by 3. At first, when I see this fraction, I don't immediately think that it's as simplified as they want, but you can do the thing where the digit sum has to be a multiple of 3, and 1 plus 1 plus 2 is 4. So we are all good.
Alright, Dorothy, you want to read the question?
Yeah, this is a long one, but I'll do my best. Square ABCD lies in the xy plane such that A is at the origin, B equals 4, 0, C equals 4, 4, and D equals 0, 4. So before we even continue, I see Arush is already doing it. I'm going to draw a picture. Oops, that is not a straight line. But I'm going to do my best to draw this square before I get lost in all the other information they're going to give me. Alright, I think I'm ready to continue. So, a line passing through C intersects the x and y axes at points P and Q respectively. Given that the points P and Q are further from A than points B and D respectively, and that BP equals 3, what is the area of triangle DCQ? Express your answer as a common fraction. Okay. So we have this line passing through C. We don't quite know what it looks like yet, so we can just draw an approximate one. What if it goes like this? Then we would have point P where it intersects the x-axis, that is here, and point Q where it intersects the y-axis, which is here. Arush, does this line I've drawn satisfy the conditions of where P and Q should be?
I think so. It says P and Q are further from A than points B and D. Oh wait, but oh no. It looks like P and Q are actually closer to A than points B and D. So did we mess it
Yeah.
up?
So I think that means we have to draw it somewhere else, because like I said, there's lots of places where I could draw it. You'll notice if my line goes through the square like this, then Q is going to be closer to A than B is. So the line has to go like out like this, sort of, to avoid that. So I'm going to draw a new line and see if that does any better. It's going to go through the question a little bit, but it's okay. Alright. So now I have this line. And I'll draw points P and points Q again. And it looks like this works because P is further than A than B is, and Q is further than A than D is. So now, Arush, what information can we still use to help us figure out what the area of the triangle is?
Well, let's see. We're also given that BP equals 3. And my diagram here is a little bit off because it looks like BP and AB are the same length. But remember that the side lengths of this score are actually 4. And so BP is actually a little bit shorter than AB. Now we want to find the area of triangle DCQ. And I'll be honest, this is looking a little scary. But usually when we have lots of right triangles, we'll have lots of similar right triangles. Now Dorothy, do you see any similar triangles?
Yeah, I'm thinking triangle QDC and triangle CDP and triangle QAP are all similar, and the reason why is they share a right angle. Well, QAP and CBP share a right angle and this angle P. So QAP is similar to CBP. And now we can use QAP and notice that it has a right angle and it has angle Q. And you know what other triangle has a right angle and angle Q is triangle QDC, which is the one we're trying to find. So QAP is also similar to QDC, which means that all three of these triangles are similar to each other. So, Arush, how do we use these similar triangles to solve the problem?
Well, similar triangles mean that the sides have the same ratios. And we already know some sides. We know DC, CB, and AB are all 4 because this is a square. And we're also given the coordinates. And we also are given that BP equals 3. So the legs of triangle CBP are 4 and 3. And so the ratio between them is 4 over 3. And I'm just going to write this, that we know that CB over BP indeed equals 4 over 3. And because of these similar triangles, given that CBP is similar to QDC, Dorothy, what else do we know CB over BP equals?
Well, we can compare the legs of the similar triangles that correspond to each other. So QD and CB are both those vertical ones that border angle Q and the right angle. So we know this is equal to QD over the side that corresponds with BP, which is DC, which is also 4. So we know QD over 4 equals 4/3. And so solving for QD, we get that QD is equal to 16/3. And I think we're almost there. Arush, can you finish off the problem for us?
Awesome. So since we know that QD, in fact, equals 16 over 3, and we know DC equals 4, the area of QDC, because it's a right triangle, is simply, I'm just going to write this out, area of QDC, in fact, equals 1/2 times 16 over 3 times 4, which equals 32 over 3. And so 32 over 3 is our final area for QDC. It's actually asking for DCQ, but these are actually the same thing. And let's check the answer. And it is indeed 32 over 3. So we got this one. Great job, guys.
Yeah, I'm seeing a lot of that in the chat, which is great. Ooh, this is a wordy one. You want to read this one out loud?
Alright, you pinned the wordy one on me. At a zoo, there are 5 types of animals: lions, tigers, bears, monkeys, and zebras. Each type of animal is kept in its own enclosure, and zoo visitors can only see the animals in an enclosure if the enclosure is open. Every day, the zookeeper opens a non-zero number of the enclosures, but he must follow the rules below. If the lion enclosure is open, then exactly 2 of the other enclosures must also be open. If the tiger enclosure is closed, then the bear and zebra enclosures cannot both be closed. The monkey and zebra enclosures can never be open at the same time. How many distinct sets of enclosures can a zookeeper open? Wow, that's a lot of conditions, and a lot of animals too. Dorothy, how can we get started?
Well, it seems like this one we're just gonna have to try things out and see what works. You'll notice there aren't actually that many different sets of enclosure out there, whether or not they're legal, because each cage or each enclosure can be open or closed. So there's 2 possibilities for each enclosure, and then there's 5 enclosures. So in total, we only have 32 possible enclosure arrangements. So Arush, I'm kind of inclined just to write out all 32 and cross them out. Do you think there's a faster way of doing this?
Oh wow, writing 32 strings out isn't that crazy. But then again, we can also do a little bit of casework. The first condition looks a little bit vague. They say exactly 2 of the other enclosures must also be open, but we don't know which enclosures they're necessarily talking about. Now the second condition says if the tiger enclosure is closed, then the bear and zebra enclosures cannot both be closed. And the third one says the monkey and zebra enclosures can never be open at the same time. That's pretty helpful. For now, I think we can represent our set of enclosures with a binary string like we saw earlier, with 1s and 0s. We have 5 animals, and I think we can write a binary string to represent which animals have their enclosures that are open and which ones are closed. A 1 will denote that the enclosure is open, and a 0 denotes that the enclosure is closed. So for example, if the lion enclosure was open, now I'll put a 1 in the first spot. And I'm going by the order that they list them in the problem: lions, tigers, bears, monkeys, and zebras. And, for example, if the tiger's enclosure is closed, I would put a 0 there. So now we have some notation to represent how we're going to denote the animals and whether their enclosures are open. Now, Dorothy, how can we get started with some cool casework?
Well, it looks like if the lion enclosure is open, that kind of makes it easier on us because we know that exactly 2 of the other enclosures must be open. That means we have to have 2 other 0s and 2 other 1s. So let's just say we have, and it's worth noting that if you have 2 0s and 2 1s, you're trying to arrange them. I believe there's only 6 ways to do this because it's 4 choose 2 where to put the 0s. So there really aren't that many. We could write out these and then just take a look, see which ones are bad. So, in no particular order.
But in fact, Dorothy, I think it's a little bit faster way to do this. Since we only have 2 closed enclosures, which condition do we know cannot fail?
Well, we also know about the second condition. So the bear and the zebras cannot both be closed, and the monkey and the zebra cannot both be open. So that's getting rid of 2 possible numbers for us. We can't have monkey and zebra both open, so this first one is bad. And we also can't have bear and zebra closed. Oh wait, that's only if the tiger enclosure is closed. And because we can't have 3 closed, we actually can completely ignore the second condition, just in this case.
And also, we know that the monkey and zebra enclosures can never be open at the same time. Since, other than the lion enclosure, we only have 2 open enclosures, there's only one bad case where the third condition fails in this specific case, and it's where we have the string 1, 0, 0, 1, 1, because here the monkey and zebra enclosures are open at the same time, which is not allowed. So out of the 6 that we can have, because we have 4 spots and we need to choose 2 of them to be closed, only 5 of them work, 1 of them doesn't. So, to summarize, when line is open, I'm just going to write L equals 1, we have 5 cases that work. But now, what's the other case? We could also have the line enclosure is closed. And now, our string would look something like, particularly, it would start with a 0. And we don't have any numbers for the other spots yet. In fact, there's no other condition that actually applies to the lion. So for now, we can just throw away the lion. And Dorothy, where can we go from here?
Well, we know that the tiger, bear, and zebra enclosures cannot all be closed at the same time. That's what the second one is saying, that you can't have all 3 closed. So that only allows us to throw out 2 cases. When, let's see, which one? When these 3 are closed and this one is open, and when all 4 of them are closed. So we can do the same sort of complementary counting. Here, the number of ways we have to start with the lion is 16. And the reason for that is we have these 4 spots, and each of those spots can either get a 0 or a 1. So we're going to do 16, and then we subtract 2 for this second condition. So now all we have to deal with is the third condition. Arush, how many should we subtract for the third condition?
Well, since we've already subtracted some cases for the second condition, we have to make sure that we don't subtract the same case multiple times. Well, if we forget about the second condition and only look at the third condition, when the third condition fails, we know the monkey and zebra enclosures are both open, so we have 1s there. Which means that we have 4 possibilities for the enclosures here. Specifically, there are 0, 1, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 1, and 0, 0, 0, 1, 1. But, if any of these violate the second condition, then we've already accounted for them. Which one of these 4 violates the second condition? Dorothy?
Well, it would be the one where the tiger enclosure is closed and the bear and the zebra enclosures are closed. So we need to have a 0 in the second spot, the third spot, and the 5th spot. So I don't think it's any of those, is it?
Exactly, because if the third condition fails, that means that the monkey and zebra enclosures are both open. But we're given that the second condition only fails if the zebra enclosure is also closed. So the second and third conditions actually do not overlap. So we can safely subtract the number of bad cases where the second condition fails, and then subtract the number of cases where the third condition fails. And the number of cases where the third condition fails, like we said, and just listed out, is 4. So Dorothy, how many total bad cases do we have here?
Well, we had 2 from before and 4 now, so that's a total of 6. We'll take that away from the 16 to get 10. So now we just have to sum together the lion's cage is open and when the lion's cage is closed. Those 2 cases are disjoint because the lion's cage can't be open and closed, and it also covers all of the possibilities because it has to be one of the 2. So we can just take this 10 and add it to this 5 for a total of 15.
Awesome job, Dorothy. I didn't really like this problem because it's a lot of casework, but sometimes you just have to bash out the casework. And if we check our answer, and now we're on slide 17 in fact, the answer is 15. We got it right, let's go.
Alright, next.
Alright. Dorothy, you want to read it out loud?
Yeah, sure. Given that x and y are positive integers that satisfy the equations xy squared plus x plus y equals 55, and x squared y plus x plus y equals 43, what is x plus y?
That's an interesting question. Well, I noticed an x plus y in both the top and the bottom. So maybe we could try, for one, subtracting them, or we could try adding them. Dorothy, which one do you think we should do?
I think I would prefer if we have fewer things in our equation, so I think we should subtract them to get rid of the x plus y's, and then we'll just get xy squared minus x squared y equals 12. And this actually looks factorable. Then we would get xy times y minus x equals 12. And so this is already looking pretty promising to me because we're given that x and y are positive integers, so there really aren't that many options for x and y if we wanted to just try out the factors of 12. The 12 does have a lot of factors, at least for the number of its size. Do you think we should just try them out, or do you have a better idea, Arush?
I think it's actually a great idea. The factors of 12 are 1, 2, 3, 4, 6, and 12. It's actually 6 factors, and there's a neat way you can show this. But what matters right now is that xy and y minus x must be in this set of numbers, and they must multiply to 12. Well, we could have xy equals 1 and y minus x equals 12, but then we need y to be greater than 12, and yet somehow still multiply by x to get 1? That's not happening. I think in fact that y minus x is probably going to be smaller than xy, so we can start with setting y minus x equal to 1, and setting xy equal to 12. Dorothy, do any pairs xy come to mind here?
Well, I'm thinking 3 and 4 would be a pretty easy one. And another way to see that they're likely to be something like 3 and 4 close together is looking at these 2 top equations. You'll notice xy squared plus x plus y is not that different from x squared y plus x plus y. So it doesn't really make sense for them to be numbers that are super far apart. It makes sense to start with the smallest possible y minus x, giving us 3 and 4. And I think this might actually satisfy the equation if we plug them in. What do you think?
I think that's a great idea. Like lots of people said in the chat, great job guys, x can equal 3 and y can equal 4. So are we done just because it satisfies in this equation right here? No, because just because it satisfies xy squared minus x squared y equals 12, it doesn't mean that each of these 2 equations are satisfied. But it's pretty easy to plug them in and check. Well, xy squared equals 3 times 16, which is 48. So the top equation evaluates to 48 plus 3 plus 4, which does equal 55. And the bottom one evaluates to 3 squared times 4, which is 36, plus 3 plus 4, which equals 43 indeed. And so these 2 equations are satisfied. Now, there is the possibility that there are other solutions, but remember, when you're in competition, you're doing the sprint round, you have to move really fast. If you know there's one correct answer, you probably know it's the only correct answer, because they only say there's one answer. So we know that the number that we want is x plus y equals 7. And we can just go ahead and submit this.
Nice. Let's check.
If we check the answer, it is indeed 7. Let's go.
Alright.
Alright, let's see. How many base 10 positive integers less than or equal to 127 have palindromic base 2 representations? Or in other words, base 2 representations that read the same forwards and backwards. Wow, that's interesting. Well, I think we should first write out some example palindromic base 2 representations. It could be something like 110, and then it has to go the same way backwards, 011. It could also be something like 11011. But what matters is that when we flip the number, it stays the same. Now, Dorothy, what do you notice about the number 127 in particular here?
Well, I think it's notable because it's 1 less than a power of 2. You'll notice in base 10, if you have 1 less than a power of 10, that's like 9, 99, 999. These are all the biggest number that has their number of digits. Like 9 is the biggest 1-digit number. 99 is the biggest 2-digit number. So similarly, 127 is going to be the biggest n-digit number in base 2, where n is something haven't quite figured out yet. But if we write out 127, we'll see that, sort of like 999, it's just going to be all 1s. And we need enough 1s until we get to 127. I don't actually know how many that is yet, but this looks about right. Let's see. So we should have up to the 64th place. We want 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. So, looks like I have 1.
I think that's a total of 7, right?
Oh, is it? Wait, 1, 2, 4, 8, 16, 32. Yeah. So basically, what this question is asking is how many base 10 positive integers are there? Or, okay, let's just ignore the base 10. How many base 2 numbers are there of 7 digits or less that are palindromic? So it's just asking how many palindromic base 10 integers with 7 or fewer digits are there. So how do we tackle this, Urush?
Well, like you said, it can have 7 or fewer digits. So I think the first idea is to actually go through every possible number of digits. And for each of them, try to count how many palindromic base 2 numbers have that exact number of digits. And note that having 7 or fewer digits actually guarantees that the numbers are at most 127. So for now, we can forget about that condition and replace it with 7 or fewer digits. Now, this means I can either have 7 digits, 6 digits, 5 digits, 4 digits, 3 digits, 2 digits, or 1 digit. Alright, I think that's looking good. Dorothy, you want to get started off with 7 digits?
Yeah, so if we have a 7-digit palindrome, I'm just going to write out 7-digit places. Whatever we put in this first spot, say it's a 1, is going to force the last digit to be a 1, because it needs to be the same when flipped. Similarly, whatever we put in the second digit place is the same as the second to last, the third digit is the same as the third to last, and then the fourth digit just has to be the same as itself. So when we're creating a base 2 palindrome with 7 digits, we really only have 4 digits that we can choose, and then the rest are forced by the condition that it's a palindrome. So we have 4 digits to choose, and we have 2 digits for each of those, a 0 or a 1. So we have 2 to the 4th ways to make a 7-digit palindrome, which is 16. Arush, how do we do 6?
But wait, but Dorothy, I have a question.
Mhm.
Is it really 7 digits if it starts with a 0? Like, for example, would I write the number 99 and 099? No, because usually the assumption is that we don't actually start with trailing zeros. Or, I guess I should say leading zeros. So we also know that the first digit must be 1. So in fact, we're only left with 3 digits that we can actually choose. Is that right, Dorothy?
I think that's true, yeah. So we need to subtract... we need to force this to be a 1, so we can only choose these 3. So we're actually only choosing 2 to the 3rd, which is 8. What about 6?
Well, I think we're going to notice a very similar, but not really similar, pattern. Now we have one less digit. I'm just going to erase this last digit, and we know that once again I must start and end with a 1. Now here, we know that the second digit must line up with the second to last digit, and the third digit must line up with the third to last digit. So we have 2 empty spots here. Remember, when we had 3 empty spots for 7, we got 2 to the power 3 possibilities, or 8 possibilities for 7. So for 6, since there's 2 degrees of freedom, or spots where we can change the number from 0 or 1, the total number of possibilities is 2 squared, which is 4. Because remember, whatever digit I put here must also go here. And whatever digit I put here must also go here. So we have 4 for 6. Now, Dorothy, what about 5?
I think 5 is actually going to be the same as 6. Because here we have every digit pairing up with another digit. But if we take away this digit at the end and make this last number also a 1, well then we have the pair and this digit by itself. So we still have 2 choices, it's just one is going to be by itself as opposed to all of the numbers being paired. So this one is still going to be 4. I feel like I'm noticing a pattern here, because the next one, we're just going to go down to 1 choice, because we get rid of another digit. So that one's going to be 2, and then similarly, 3 is going to be 2, because now that digit is just paired with itself. 2, well, now we have no more choices, so that's going to be 1. And 1, I think now we can do either 1 or 0. Does that make sense? Oh,
But wait,
no, it says
we're also
positive.
given that's a positive integer.
True.
Yeah, so in fact, we cannot have 0 digits. Or I guess 1 digit case only has 1 possibility. So all that's left is to add up all these numbers. And like lots of people have already said, 8 plus 4 plus 4 plus 2 plus 2 plus 1 plus 1 does indeed equal 22. I have to do it in my head quickly. And so the final answer is 22, and we're done.
Cool.
And the answer is indeed 22, so that's great. Dorothy, you want to take it away with this question?
Yeah, so we have some positive integer x, where the quantities 2x plus 24 and 20x plus 24 are both perfect squares. I wonder if this was written in 2024. It's kind of uncommon for a 2026 question. But what is the second smallest possible value of x? So I think a nice way to start this out is just to assign these perfect squares that they're equal to names. So let's just say 2x plus 24 is a squared, and 20x plus 24 is b squared. Now, Arush, what can we do with these equations?
Well, in fact, I think we can actually subtract them to cancel out the 24. If we subtract them, then we're left with 20 minus 2x equals b squared minus a squared. And so 18x equals b squared minus a squared. And we can try factoring this using difference of squares. But it seems a little bit complicated. Dorothy, what are some alternative possibilities?
Yeah, I mean, normally when I see difference of squares, I'm inclined to factor, but then we have a lot of things going into 18x, which might not be that easy to solve. So another alternative could be to solve for x in terms of a, or to solve for a in terms of x. Just manipulate these equations here to get them into some form that we can plug into the other one. Here I might solve for x in terms of a because we notice this x in both equations. How does that sound to you, Arush?
That sounds like a good idea. Alright, so if we try to solve for x, we're going to get that x equals a squared minus 24 over 2, which equals a squared over 2 minus 12. And similarly, if we plug into b squared, we're going to get that 20 times this plus 24 equals b squared, So multiplying by 24, we get 10a squared minus 240 plus 24 equals b squared. So if we take the b squared to the other side, we could try to do difference of squares, but it's a 10a squared, not just a regular a squared. Dorothy, what do you do instead?
Well, I feel like we have some other handy equations. Maybe we could use these to get rid of the a or the b, or we could also just try plugging in values here, I think, because we're just trying to find the second smallest possible value of x. What do you think?
Well, I think for our first step is we know that, 10a squared must end in a 0, and 240 plus minus 240 plus 24 ends in a 6. So b squared must end in a 6. So we know that b itself ends in either 4 or 6, because these are the possible units digit that will yield a units digit of 6 for b squared. Well, that doesn't actually limit our possibilities a lot. What do we do now?
Well, I think we could also observe that a is going to have to be an even number here. That might help us somewhat, because we have a squared over 2 minus 12 is x. So if a is an odd number, then x isn't an integer. So we could just cut things down a little bit by replacing a squared with something like 2k. And so that way, we know that we're not going to be checking possibilities that can't work. Because we don't want to be checking or plugging in things for a that are odd that might actually get us a fine answer in this bottom equation that don't work. So let's just say, instead of 10a squared, we have 40k squared equals b squared. And now I'm wondering if we can just plug in some things for k and try to find a perfect square. What do you think?
I think it's actually a pretty good idea, but we might have some pretty large numbers. Remember, we subbed in that a equals 2k, so we can rewrite our expression for x to be 2k squared over 2 minus 12, which, like Dorothy said, is simply 2k squared minus 12. And, some possibilities for k might be 1, 2, 3, 4, 5. Who knows?
Yeah.
Well, the first thing we can do is, since the left-hand side is a multiple of 4, b must also be even. So, we could replace b with something like, 2j.
Might as well.
And if we replace with 2j, we can cancel a lot of 4's, which will work out in our favor. So, when I replace it with 2j, I'm going to get 4j squared, because 2 squared equals 4. And then when I simplify, I'm going to get k squared minus 60 plus 6. And I can just reduce this to k squared minus 54, 10k squared minus 54 equals j squared. Is that right, Dorothy?
Yeah. And I feel like it really can't be that hard now to plug in values for k, because we know that k can't be just 1, because then 10k squared minus 54 is j squared, so j squared is negative. That's not possible. K can't be 2. And so I'm hoping we're going to run into a square pretty soon. Do you think that's going to happen?
I think we're going to go to square really quickly, depending on the answers we got in the chat too. Well, the next one we have is k equals 3, because k equals 2 gives a negative j squared, and squares can't be negative. So if we have k equals 3, then we have 90 minus 54, which is 36.
Oh.
Is that a possibility?
Yeah, 36 is 6 squared, so it sounds like that will be our smallest possible value of x.
But Dorothy, we want the second smallest possible value of x, so we need to keep going.
Yeah.
Well, now k could equal 4. But if we have k equals 4, then 160 minus 54 is 106. So 106 is not a perfect square. But now k equals 5. And if we have k equals 5, 250 minus 54 equals 196, which is equal to 14 squared. So we have k equals 5 and j equals 14. Now since our expression for x is 2k squared minus 12, if we plug in 5 for that, we get 2 times 5 squared minus 12. And 2 times 5 squared minus 12 is equal to 15 minus 12, which equals 38. And so we're done. And in fact, this was our last question for today. So great job, guys.
Yeah. It's worth noting for this, it's true that bashing is annoying, but we tried to make the bashing as minimal as possible by introducing these different variables and sort of narrowing down the cases. So I think something like this you will have to bash a little bit, but hopefully not that much.
You know, in fact, if you want to keep going, you could even divide out the 2 and notice that j must be even too. So you can replace j with another variable and keep on going till it became really simple to solve. But here we already found the answer, and we can check it to see that it is indeed 38. And so we are done. Great job.
Yeah, well, I think that's all we have time for today, but thank you guys so much for coming to our live solve. It was really great having all the participation in the chat and everything.
This was really fun, so thank you so much, guys. Bye.
Bye.